In this session, we're going to see some basic applications of exponential functions, and we are going to dive right in, starting with the compound interest formula, which is a is equal to p times the quantity of 1 plus r over n to the nt. This is not something I would ask you to memorize, but you're going to see how we're going to use it, and that's what I want you to know. This formula is used for what we call discrete or periodic compounding. Compounding is what happens when interest gets added to what you owe, and then you start paying interest on interest. That's called compounding interest. If we can say how often that happens, 4 times a year, 12 times a year, then we use this formula. Our first example is going to be to find the value of a $6,500 investment after 15 years if it earns 7.25% interest and is compounded first annually. Let's see how this fits with the formula that we've been given. The P is the amount that's invested or borrowed. And in this case, we're talking about an investment, and so the $6,500 is going to go in place of P. The T is the amount of time that it's invested for, and so in this case, the time is going to be 15 years. R is the interest rate, and in this case, we're looking at 7.25%. We need to turn that percent into a decimal, and so R is going to be 0.0725. Okay, so whenever you're given a percentage and you need to use it in a formula, it needs to be converted to a decimal. Then there's the N. N is the number of times it compounds per year. And so for part A here, annually compounded, N is equal to 1. That means once a year, the interest that you have gets rolled up into the new principal, and then you start paying interest on interest. Or in this case, start earning interest on interest. This is just going to be a matter of plug and chug, as I like to say. So A is equal to the $6,500 that's being invested times 1 plus, okay, now R is 0.0725 divided by N, which in this case is 1, but I'm still going to write it to flesh out the formula. End the parentheses, and then to the 1 times T, which is 15, according to what was stated in the problem. At this point, this is simply a calculator exercise. So when I put this into my calculator, I get that A is approximately $18,572, that needs to be a comma, and about 61 cents. With money, we're going to round off to 2 decimal places because that makes sense. What I need you to do is make sure that you can put this expression into your calculator and get the answer that I just wrote down. Well, let me circle that as the answer and then move on to the next part, which is asking us to figure out the same investment, but now we're changing the N. We're now going to be compounded quarterly, and since there are 4 quarters in a year, we're now looking at N is equal to 4. It's still the same formula, and so our A is equal to 6,500 times the quantity of 1 plus 0.0725 over now 4 to the 4 times 15. And as we go through these, you're going to notice that the nt as the exponent in the formula, which in this case is 4 times 15. If it's compounding 4 times a year over 15 years, then it will compound 60 times. And so the exponent is actually the number of times it compounds in the time period. Well, let me put this into the calculator. And this time I get that the amount is approximately $19,097.63. It's not a big difference from 18,572 to 19,097, but the point is that the number of times that it compounds per year does make a difference. Next, if it's compounded monthly. Since there are 12 months in a year, we're looking at n is equal to 12. And what I'd like you to do is pause the video and crank this out. So I've got a is equal to 6,500 times the quantity of 1 plus 0.0725 divided by 12 to the 12 times 15. And I get a total of approximately a equals $19,221.51. And again, you're going to say, well, that's not very much different. No, it's not. But in the real world, some people care. Finally, what if this was compounded daily? So in this case, n is going to be, we're going to use 365 days. Sometimes they use 360 or something, but we're going to use 365. So go ahead and crunch the numbers. And I'll spare you reading the whole thing. I'll just say we put 365 in place of n in the formula, and I got that the amount we have is approximately $19,282.43. So this is an example that we see where n goes from 1 to 4 to 12 for monthly and 365 for daily. We could talk about compounding every minute, every second, every nanosecond. N is getting really, really big. And this actually leads us to the next idea, which is Euler's number. Euler's number is represented by E. Its value is approximately 2.718. And it's the value of the expression 1 plus 1 over n, that quantity to the n, as n approaches infinity. Thus, as n becomes larger and larger, the expression that we were just looking at, 1 plus r over n to the nt, becomes e to the rt. And from this, we get the formula for continuously compounding interest, and this is where I want you to pay attention. A equals pe to the rt. And so using this, what we're going to do is find the value of a $6,500 investment after 15 years if it earns 7.25% interest if it was compounded continuously. The $6,500 is the same as before. It's the P that was invested in this case. Could be borrowed, but in this case invested. The 15 years is the time T, and the interest rate, 7.25%, is still going to be expressed as a decimal, 0.0725. But now, because it's being compounded continuously, we are going to be using PERT, A equals PE to the RT. This formula you need to memorize. The other one, I just want you to know how to use. This one, I need you to memorize. It's going to be used in several different contexts. Well, let's see how it gets used. A equals, in this case, 6,500 times E. Now that's a button in your calculator. And then R is 0.0725 and T is 15. So there are some similarities to the other formula, but this piece where we have 1 plus R over N to the NT becomes E to the RT. And the details of that, it's really a calculus notion. When you see anything like n approaching infinity, that's a calculus notion. I just need you to know the result. A equals PERT. Well, now as far as calculator stuff goes, the $6,500, or the 6,500 in the expression, is a coefficient. And so that's not part of the base because there basically aren't parentheses around the 6,500 in the E. Okay? What you need to let your calculator know is that the 0.0725 times 15 is all one exponent. Now, some calculators are such that you need to put the exponent in first, and then you would hit your e to the x button. For other calculators, you hit your e to the x button, and then you put your exponent in. It's up to you to figure out how your calculator works. If you need to, I can talk to you about that individually. But for right now, to check on your calculator, essentially, I'm going to crank out the number, and I get that A is approximately $19,284.51. I need you to round correctly, and it'd be good to identify money using a dollar sign. Next, find the value of the same investment with the time is 9 years, 3 months. So now we're messing with the time. 9 years, 3 months. How do we do that? The time is going to be 9 and 3 out of 12 months, or 9 and a quarter, which I'm going to call 9.25. So now we've got, it's the same investment, and so it's the same $6,500. E is just featured in these continuous compounding problems. The interest rate isn't what's changing, 0.0725, and then now 9.25 is the time. And so putting this in my calculator gives me that the amount is about $12,710.48. Oh, dollar sign. That's that. Oh, I forgot to make the approximate in the second one, so it should be approximately equal. Sorry about that. Now we've got another example. A particular colony of bacteria grows in number according to the function n of t is equal to 1000 e to the 0.01 t, where t is the time in minutes. And we're to find and interpret some function values. Here's what I want you to notice. This has the same structure as A equals PE to the RT. Okay, this has just got different symbols, but it's really the same function. This is what I mean when I say it's used in different contexts. Well, n of 0 is going to be what happens when 0 is put in place of t. The reason I know that, by the way, is that n of t is function notation, where t is the input variable. I also recognize that e is a number, and so there's only one variable in this expression, and that is the t. So n of 0 is going to equal 1000 e to the 0.01 times 0. That makes an exponent of 0. This gives me an answer for n of 0 of 1000. Now, interpret. Okay, t is the time in minutes. If t is 0, then no minutes have passed. This is going to be the starting number of the colony. In other words, the 1000 is the initial population of the bacteria, or the original number in the colony. For n of 1, we're going to use 1 as in place of t, and so n of 1 is 1000 e to the 0.01 times 1. That calls for a calculator, and mine is telling me that n of 1 is approximately 1010.05. Okay, you can't really have 0.05 of a bacteria. That'd be 1/20th of a bacterium. So I'm going to say this is 1010 bacteria. We're to interpret this, and so this is the number of bacteria after, now t is the time in minutes, and so after 1 minute. Now we can actually, we can explore this a little further, but I'll just suffice it to say that after 1 minute, the number of bacteria increased from 1000 to 1010. 10 happens to be 1% of 1000, and the exponent happens to contain a 0.01. This is actually the growth rate, and in this case represents 1% per minute. And so for those who are savvy with this sort of thing, when one looks at n of t equals 1,000 times e to the 0.01 t, one immediately knows certain things. One is that the initial population of the bacteria is 1,000. The other is that the growth rate is 1%. I wouldn't know from this equation whether the time was in minutes or in hours, and so I need to be told that. But once I know that, then I can interpret the results. I'd like for you to find n of 4. So go ahead and pause the video and figure that out. So substituting 4 in place of t and crunching the numbers in the calculator, I get that n is approximately 1,041. Again, we're rounding off because these are live critters. And interpreting, this is 1,041 bacteria after 4 minutes. Okay, so it may seem like they're not growing very fast, but as you recall from the graph of exponential functions, exponential growth may start out slow, but then it grows exponentially. That's why they refer to things using exponential growth. And for this reason, as time passes, if a bacteria has infected you, the amount of bacteria that you experience or that exists in your body over time, it grows exponentially. This is why you kind of feel like, oh, I may be sick, and then I think I'm really sick, and then, oh my gosh, I'm really sick. It's because the bacteria or your virus in your body is growing exponentially. Finally here, find n of 69.314. I know it's weird, but go ahead and pause the video and see what you come up with. And so putting 69.314 in place of t and asking my calculator for the value and then rounding, I get 2,000. So starting with a sample of 1,000 bacteria after 69.314 minutes, we get 2,000 bacteria. What this means is that 69.314 minutes is the time it takes for this population to double. And as a fun little game, what you might do is see what would happen with the numbers if you started out with a different number of bacteria. In other words, change the 1,000 to different numbers. In each case, put 69.314 in place of t, and what you'll find is it's always going to double. It's irrespective of the number that you started with. Kind of weird and freaky. Let's move on. A sample of carbon-14 decays according to the function a of t is equal to 80 times e to the negative 0.000121 t, where t is the time in years and a is in grams. This is crazy. Radioactive decay occurs in ways that are predictable. They even build clocks based on it. I don't want to get into all the chemistry. Ask me in class. It's a great discussion. But suffice it to say that the number of grams that one has in a sample that is decaying radioactively is given by this particular formula. The negative 0.000121 is a decay rate that is unique to the substance. So that's not a constant that's always there. Just like the bacteria, there is a rate associated with the particular situation. What I need you to be able to do is find a of 0, and that's what really matters. Let me make a note, though, and it is that this function is really of the form a is equal to pe to the rt. You see, it's the same function, but it's got different symbols again. A of 0 is going to be what happens when 0 is put in place of t. This time t is in years, but that doesn't matter really for the first one. A of 0 is going to be 80 times e to the 0.000121 times 0, and so the portion that has the exponent is going to be 1. And so A of 0 is equal to 80. Since I was told A is in grams, this is 80 grams of carbon-14 initially. In other words, this is how much was radioactive material when this process started. Part B, A of 10,000. So go ahead and, you know what you're doing. Put it into your calculator and see what you get, and see if you can maybe write down some words as to what this means. So go ahead and pause the video and do that. Okay, so putting 10,000 in place of T, I get that A of 10,000 as a calculator value is approximately 23.85, I'll say 58 grams of carbon-14 after 10,000 years. What folks use this for these days is they'll measure how much carbon-14 is in a sample, and according to a function that's predictable, they'll use that to figure out how old the sample is. We'll see how to do that in a different video. For now, I'll just circle that answer. Here, though, you may notice that we started out with 80 grams, and now we have 23 and some change grams. What's going on? This is decreasing over time. That's because it's decay. And in this case, as far as we're concerned, what's making this decay is the negative that's in the exponent. What that serves to do is, if you recall, a negative in front of an argument will take a graph that would have, say, grown and flips it about the y-axis, and so turns it into a decay situation. Next, we're going to look at A of 5,730, and so what I'd like for you to do is pause the video and crank that out, see if you can figure out what that means. So plugging in 5730 in place of T, I get that A of 5,730 years is about 39.992, what is that, 7 grams. Let's go ahead and round that off to 40 grams. Now we can see that while we started with 80 grams, we now have 40 grams after 5,730 years. Since it's the time that it takes for half the sample to radioactively decay, this 5,730 years is what's known as the half-life. And as with the rate, that is unique to the substance, and it is denoted by the Greek letter lambda. This is something that we are going to, again, see in more detail in another video. I just wanted you to see an example or an application of an exponential function. Here's another one. Newton's law of cooling states that a warm object cools exponentially over time. If a cup of coffee that is 170 degrees Fahrenheit is placed in a room with a temperature of 70 degrees Fahrenheit, the temperature after t minutes is given by this function. T of t is equal to 70 plus 100e to the negative 0.045 t. Do not memorize this particular function with these numbers. We're going to see more examples involving this type of formula in another video, but for right now, what I want you to note is a couple of things. One, 70 degrees Fahrenheit is where the 70 in the formula is coming from. Number two, the difference between 170 degrees, the coffee, and the 70 degrees, the room, is 100, and that's the coefficient on the exponential term. The 0.045 that's negative in the exponent, that is something that would be determined experimentally. That is, you would, in a real world situation, a coroner, because, you know, a warm object, a body could be a warm object. A coroner would maybe poke the liver, figure out the temperature. After a while, poke the liver again, figure out the temperature. From that, figure out what the constant would be, the 0.045 in this case. And then could use a formula to figure out when the body stopped breathing. I know, morbid, isn't it? Here, all we're asked to do is find the temperature of the coffee after 5 minutes, 10 minutes, and 20 minutes. Well, the time is t in minutes, and so for part A, we're going to let t be 5. Notice there's an uppercase, and that's for temperature. And then there's a lowercase t, and that's for time. And time is the input variable. And so we're looking at t of 5 is equal to 70 plus 100 e to the negative 0.045 times 5. And I've switched from red to green for the time, and it was because I wanted you to see that red denoted a subtraction difference, and all that. Anyway, go ahead and put this into your calculator and see what you get out of it. Pause the video and do that. And I get that t of 5 is approximately, we're going to say 150. Since the t is temperature and we're given Fahrenheit, this is 150 degrees Fahrenheit after 5 minutes. Oh, we weren't asked to interpret that, but that's okay. We can say it after 5 minutes. Okay, I don't know if coroners really do that, but that's how I envision this happening from my knowledge of math textbooks. All right, back to our regularly scheduled programming. We are now to find in part B the temperature after 10 minutes. Go ahead and crank that out. Pause it, do it, and putting 10 in place of lowercase t, I get that t of 10 is approximately 130, I'm going to call it 134 degrees Fahrenheit. And now you're going to ask me, how many decimal places do you want? I'll tell you on a test. For now, just be able to crank the numbers out. Last but not least, after 20 minutes, what's the temperature of this coffee? So what I want you to do is find t of 20. Go ahead and pause it, do that. And I get that t of 20 is approximately 111 degrees Fahrenheit. This is probably not interesting coffee anymore.